Bismillahirrahmanirrahim. My dear students, hope all of you are doing well with your family members. This is Irene Parveen. Once again, welcome to Chemistry First Paper class, English version arranged by KPB School and College. In the first 5 lectures, we completed up to Hund's rule. You already attended an exam on it. So let's start our sixth lecture. Our today's content is applications of electronic configuration. And under this topic, today I will discuss about determination of valency and valence electrons of an element. Number 2. Position of elements in a group of a periodic table. And 3. Position of an element in subgroup in the periodic table. And lastly, position of an element in the period in the periodic table. Electronic configuration of an atom has many applications. First, I would like to discuss determination of valency and valence electron of an element. The combining capacity of an atom is known as its valency, that is, the outermost electrons present in an atom that take part in the reaction is expressed by the valency of the element. On the other hand, the number of total electrons present in the outermost principal energy level of an element is called the valence electrons of that element. For example, the electronic configuration of hydrogen is 1s1. Here, hydrogen has one electron in its outermost energy level, and during bond formation, hydrogen atom use this electron also. So, the valency of hydrogen is 1 and its valence electron is also 1. Now another example. For oxygen atom, the outermost energy level is second energy level and there are total 6 electrons. Look here, the outermost energy level for oxygen is second energy level and there are total 6 electrons here. So, oxygen has 6 valence electrons, but the outermost 2 electrons of oxygen share with 2 electrons of 2 hydrogen atoms, forming 2 covalent bonds in water. Look here, the outermost 2 electrons of oxygen share with 2 electrons of 2 hydrogen atoms, forming 2 covalent bonds in water. So, oxygen is divalent, that is, the valency of oxygen is 2. Now, I would like to discuss the Second application of electronic configuration. We can also determine the position of elements in a group or periodic table by using electronic configuration. Elements are arranged in a periodic table vertically in a group and horizontally in a period depending on the electronic configuration of that element. And the number of electrons present in the outermost orbital of any element indicates its group. I repeat it again, the number of electrons present in the outermost orbital of any element indicates its group, and there are some rules for identifying the groups. Rule 1: if outermost s orbital contains 1 to 7 electrons, then the elements takes place in group 1 to group 7. For example, sodium atom contains only 1 electron in its outermost level. Look here, the outermost level of sodium atom contains only 1 electron. So, sodium is the element of group 1. Now, another example, for chlorine, the outermost s and p orbital contains 7 electrons, and that's why chlorine belongs to group 7. Now, rule 2: if outermost s and p orbital contain 8 electrons, then the element is grouped in 0 group, that is, the element is inert gas. For example, argon. From the electronic configuration of argon, we can see that the outermost s and p orbital contains 8 electrons. So, argon belongs to group 0. Now, rule 3: if the outermost energy level of an element consists of an s orbital which is preceded by d orbital in the inner level, then the total number of electrons of these outermost d and s orbital indicates the number of group of that element. For example, chromium. From the electronic configuration of chromium, we can see that here the outermost s and its preceded d orbital contains total 6 electrons. That's why chromium belongs to group 6. Now, rule 4: if the d and outermost s orbital contain more than 10 electrons, then in that case only the electrons present in s orbital indicates the group number of that element. D orbital is not considered here. For example, chromium. From the electronic configuration of chromium, we can see that the total number of s and d orbital total number of electrons of s and d orbital is 11, which is greater than 10. So, in this case, we can consider only the electron of s orbital, and here s orbital contain only one electron, so group number of copper is 1. Now I would like to discuss position of an element in subgroup. At first, I will discuss about a subgroup. If the outermost level of an element has no d orbital and the last electrons enter s or p orbital, then the element is placed in subgroup A. For example, chlorine has 7 electrons in its outermost level and has no electron in d orbital. So, chlorine is placed in subgroup A, and look here, the outermost level of chlorine contains total 7 electrons, and there is no d orbital here, so the group number of chlorine is 7a. That means chlorine belongs to subgroup A. Now I will discuss about B subgroup. If the last electron of an element enters into d orbital, then the subgroup will be B. For example, scandium. Here the last electron of scandium enters into d orbital, and d and s orbital total contains 3 electrons. So, scandium belongs to group 3b. Now, another example, zinc. The last electron of zinc also enter into d orbital, and the total number of electron of d and s orbital is 12, which is greater than 10. That's why in this case we only consider the electron of s orbital, and here s orbital contains 2 electrons. So the group number of zinc is 2b. Now I discuss about position of an element in the periodic table. In the electronic arrangement of an atom, the highest shell number indicates the period number of that element. For example, sodium. From the electronic configuration of sodium, we can see that the highest shell number of sodium is 3. That's why sodium belongs to period 3. Now another example, potassium. From the electronic configuration of potassium, we can see that the outermost shell or highest shell number of potassium is 4. That's why period number of potassium is 4. So that's all for today. I hope this class was easy enough to understand, but even if you don't understand any particular point, please feel free to comment down below about your questions. I will try to answer them all. No more today. Take care of your health. Goodbye.